For being here. We are absolutely honored and thrilled to have Gerry Griesel here from Nevada Gold Mines. I know this is going to be a geology theme, heavy talk, but I'm glad to see environmental scientists here as well. As Gerry was telling us last night, the company hires almost as much environmental scientists as they do geologists, so it's got direct applications to both of our programs. And we're excited that Chico State is it's being recognized also by Nevada Gold Mines, because we're upping our economic geology theme in our department, and so this is really exciting for us to be here and hearing Gerry's talk about his experience with the Nevada Gold Mine and the world famous Carlin Trend in Nevada. Gerry was telling us last night that as soon as he got out of school, he took the first job available around in Washington State and worked on a landslide that some of you 101 and 102 students know about in Oso, Washington. And he was one of the first people to work on that. The point being is that he jumped at a great opportunity, and he got there, and he was sitting in the very same shoes that you're in right now. So with that, I will hand it over to Gerry. And again, thank you very much for being here.
Yeah, thanks for having me. Really stoked to be here. I'm an exploration geologist with Barrick and Nevada Gold Mines. So just a quick explanation on that. It's a little confusing. It's like, wait, which company do you work for? The answer is yes. Up until about 4 or 5 years ago, all of the big Carlin type systems in northern Nevada were operated either by Barrick or by Newmont, two different companies, and they literally were butted up right next to each other. And finally, basically the shareholders who owned shares in both of the companies were like, get it together, stop fighting against each other. And we formed this singular company, Nevada Gold Mines. So now we control all the assets in northern Nevada. And basically they said, who has more gold in the ground, Barrick or Newmont? And Barrick did, so Barrick became the operator. So I'm fortunate enough that I get to work on Nevada Gold Mines projects, which I'm going to be talking about today. But whenever I work outside of that Nevada Gold Mines box, I also get to work on projects all over North America. So I literally have one of the most lucky, amazing jobs of anyone in the entire company. I get bounced around. Basically, they go, oh, we have an early stage project that needs geologic mapping and sampling and structural interpretation. We'll send Gerry. And they send me there for 2-3 months at a time. I work on stuff, make maps, and then I go to the next project. Finally, when the snow begins to fall, then I wind up going back and working on our existing projects in Nevada and go and help out various sites with structural interpretations and really work where all the gold is. So just a little quick background on me, like how did I get here? So I was in community college. I needed one more science class to get my associates. Geology sounded way easier than physics. So I took geology, loved it, and then had to take a year of physics. Great job. Then structural geology, we had the opportunity at my university, you could take your structural geology class as a 3-week field course before the fall term started. So rather than spend an hour a day in lectures, I spent 10 hours a day in the field collecting samples and collecting structural data and then plotting things on a tracing paper stereo net and a map by headlight at a picnic table for 3 straight weeks. And we drank a lot of beer too. So then I was like structural geology hooked, and then I went to grad school and I did structural geology. I had no clue what I was going to do. I figured I would just be resigned to working from some environmental geotesting, compaction type stuff. Those are the jobs that you have in Western Washington with a geology degree. And I did my geochronology up in Vancouver, and the guy doing my geochronology was like, oh, you should go work for a mining company. They love structural geologists. And I looked at him and said, there are still mines? Because when you live in Western Washington, you don't really realize mining and economic geology is a job opportunity. So I was like, oh, that sounds great. 3 weeks later, an alumni came to my university right before I was defending my thesis. I signed up for an interview, offered me a job. I started doing mapping for economic geology right then and there. And then how did I wind up here? So I met Shapiro. He was one of the teachers on one of a field camp class that we were hosting at one of our mines, and we both had Grateful Dead patches sewn to our field gear. So we hit it off instantly. And then the why am I here? Well, that's funny. Basically our company realizes we're doing a horrible job. We used to be a lot better at this, at reaching out to universities. and trying to work projects with the universities and recruit people, for potential careers, and also to work on projects. So we worked with some of Hannah's students on an undergraduate project doing petrography on one of our deposits, kind of in the northwestern part of our area. We hired one of Russell's grad students last year to come work at one of our mines, and then Erica, who some of you may know, she came and interned with us this summer, and now she's going to be doing a master's project with us at the School of Mines, right? So this is just us wanting to kind of reach out and just show people that there are job opportunities for us, and also just to kind of show what you can do with your career. So with economic geology, you use everything: stratigraphy, structural geology, intrusions, metamorphisms, paleontology, everything. We're basically a jack of all trades and a master of none. But we literally have to use every little bit of geology to kind of put these stories together and piece it together. So there's a lot of different kind of job opportunities. We can literally hire people right out of school. You can come work for us as a career, move you out to Nevada, and basically have a full-time career path job that sets you up. We also hire temporary contract positions, a lot. We just have projects, a mapping project up in Canada, something out in western Nevada. We just need someone to come log core for us for 6 months, and we just offer a contract. And we'll literally call up your professors and be like, hey, who's the sharpest bunch? Like, would they be willing to come log core for us for 3 months? So just kind of wanted to let you guys know that there are opportunities like that. We have to put this up there. Some message from my sponsors. Real quick, a little bit of shameless promotion. This is just some of the horrible places that I'm stuck working in as an exploration geologist. It's up in Northwest Ontario, a project we're working on this summer. This is up in southwestern Montana, a new project that we got into this year. So I spent actually the last 3 months doing geologic mapping and sampling out here. And then this was last year actually in Greece. So one of the beauties of being in the exploration group when you work for a global company is every kind of 3 to 4 years we have these big technical workshops, and groups of us from all over the world. These are my colleagues that work in South America, Africa, Europe, North America. We actually get to go on about a week-long trip and go visit ore deposits. So I unfortunately had to go to Greece and work on these, go check out all these massive undeveloped high sulfidation and porphyry systems. Behind us here in this cliff is actually literally a porphyry deposit. There's all the vein types and alteration systems sitting right there in the water. It'll never be developed for obvious reasons. It shouldn't be, but it's a beautiful spot to just literally stand on the Aegean Sea and go, wow, this is what a porphyry system looks like. All right, so this talk specifically, though, we're going to talk about Carlin type gold systems. So we'll kind of talk about what a Carlin type system is. We'll look at what the macro scale tectonic framework looks like in Nevada, because that's a really critical piece of all this. And then we're going to look at the rheology of the rocks that host these gold systems, because that plays a fundamental role in kind of describing how these rocks break into form and how that resulting deformation can wind up trapping gold mineralization. And then finally, we're going to zoom in. This is a much bigger talk that talks about all Carlin systems. But we're going to talk specifically about the Carlin Trend, because a handful of you will be going there tomorrow. And my colleagues there will be leading you on a fantastic tour and showing you guys what these deposits look like. You're going to have an opportunity to look at drill core of these things, and they're a really fun exercise put together for you. So this will be kind of a good introduction as to the steps that have prepped these rocks and allowed them to host so much gold. Okay, a Carlin type system is a couple things basically to sum it up. It's sediment hosted gold, it's invisible gold, and the gold is actually locked up in the framework of sulfides. So most of us, when we think of gold, if you have no background in economic geology, the first thing that probably pops in your head when you think of what does a gold system look like, you're probably going to picture some big quartz vein that has visible gold in it. That happens in deep, kind of more metamorphic conditions. This is stuff that happens really in the really shallow portion of the crust. And so this diagram up here is just a schematic thing that a colleague of ours put together about 20 years ago. Francois Robert was his name. He's retired now. And it's a simple schematic representation of hydrothermal fluids which contain gold coming up into a limestone host and showing an alteration up along a high angle structure and showing an alteration halo around it. And unfortunately, this graphic was kind of taken as, this is what a Carlin system looks like in the literature for 15, 20 years, when it was only ever designed to be a simplistic schematic representation of what an alteration halo looks like. So we're going to actually kind of dig into the nitty-gritty of the more complicated structural relationships that you actually need to put in place to build one of these systems. The gold system itself, this is from a paper that John Montine at UNR, Nevada Reno, put together, I think in 2018. And it's a really good diagram of how the gold system actually works out. So the sediments that these systems are hosted in are carbonate rocks, but they're not clean carbonates. They're not the clean, easy limestones that in Geology 101 and lab is like the one rock that you can ID because it had big crystals and it reacts with acid. These are carbonate rocks that actually formed out on the slope. So they transported carbonate grains. And that makes them very dirty carbonates by nature. So instead of just having pure calcite or pure dolomite, you also get little bits of quartz and feldspars mixed in. And this is pretty important, most of them have diagenetic pyrite in them, which means it's pyrite that actually formed when the sedimentary process was taking place. Now, we take that, we deposit it, we make it a rock, millions of years go by, and we pass a bunch of gold-bearing acidic fluids into this carbonate, and that acidic fluid winds up eating out the carbonate grains themselves, increasing the porosity of it. And when it does that, it releases iron out of that carbonate lattice. And the important thing is there, it has to be iron 2+. If it's iron 3+, gold wants nothing to do with it. So now you have this iron 2+, it's free and open in solution, and it mixes with the gold, which is transported via sulfur and hydrogen in that fluid, and it has a chance to react and form on as microscopic rims. These are like 10 micron sized little rims, and these are SEM images of them. And so it reacts with the sulfides and forms a mineral called arsenian pyrite. And it's so small that so these little arrows kind of point in, these tiny little rims around these little grains. And hence, this is the invisible gold portion of it. The most experienced Carlin geologist in the world, you could hand him 2 rocks, and I could look at it and go like, that one might have gold in it, and that one might not. And I got about, I don't know, 30% chance of being right, despite it's a 50-50 shot. So this stuff is very, very, very blind. So to find it and understand how it works, you need to be able to look for really altered rock in the right structural setting, and then send it off to the assay lab and hope it comes back with gold in it, because you're never going to be able to look at it visually and say, not until you basically have worked on that deposit and you've seen a ton of the rocks come out of the ground, and you finally learn that specific little deposit, then you can finally be like, all right, that's going to be gold. But then you go to the next deposit, 10 kilometers away, and you got to learn that whole process all over again, because they're very, very unique. Okay, so this is a cartoon description of basically a Carlin type system as a macro hole. To form any sort of mineral deposit, you kind of need 3 things, and it doesn't matter, this is for any metal. You need to have a system, you need to have a structure, and you need to have a host. Okay, the system is just some sort of big engine that has the ability to drive massive amounts of fluid through rock. So think of it like, I think the easiest way to think of this is if you have a whole bunch of people that are trying to get somewhere, but they can't get anywhere, they need a way to get there, right? So in this case, the metaphor would be, okay, if we put all these people in a car, then they have the ability to get somewhere. The engine for most mineral deposits is some sort of massive intrusive body that has enough heat, and the metals will either be dissolved in the actual magma itself, or the fluids that it interacts with, or the fluids that come off of that intrusive body. You can also do this with metamorphic fluids. So now we have our system. We have some way to drive a massive amount of fluid where there happens to be gold there, but it has to get somewhere. And that's the structure part. So think of the structure as the interstate highway. You can have all the cars you want in the world, but how are they going to get anywhere if they don't have a highway to get there? So you need a structure to transport those fluids, and typically it needs to be a big structure. So just like with traffic, if you have a 1-lane road and thousands of cars, you're not going to be able to really get people very far. But if you have a 10-lane freeway, i.e. a really big structure, then you can transport a lot of fluid a long ways. And finally, you need a host. So for any sort of system, you need to have some sort of a host that can change the chemistry of that fluid. Otherwise, it's going to just remain in the fluid. So you need to change the temperature, you need to change the pH, you need to change the pressure, or maybe all three. In the case of a Carlin system, these structures are brittle faults. They can be high angle and they can be low angle. Our host is these carbonate rock units, these dirty carbonates. And the structures, you need to have kind of more than one piece to these. You need to have a pathway for the fluids to go, but then you also need to have a trap to keep those fluids in place. If the fluids just make it all the way up to the surface, then it's some sort of, it's either just fluid emitting as a steam or it's a volcanic eruption, and you don't have an ore deposit. So our traps can be folds, they can be thrust faults, they can be dikes, they can be sills, or they can just be an impermeable layer of stratigraphy, or it can be some combination of all of those. So the macro picture then for a Carlin type system is you wind up sitting these next, they're always sitting next to, in Nevada anyway, some sort of Mesozoic intrusion. There's always a bunch of high angle structures which have long-lived history. They've probably been a normal fault, reactivated as a reverse fault, and then reactivated as a normal fault. And all across Nevada, all of this carbonate stratigraphy sits underneath the Roberts Mountain thrust, which has taken deep silicious rocks and thrusted over the carbonate stratigraphy at the onset of the Cordillera and erosion. So we kind of, in the business, we kind of talk about two different types of Carlin type deposits. We have these more strata-bound ones, which are kind of, 20 to 50 feet thick, and they just follow a really nice, favorable limestone bed. Or we have these more high-angle, quote, structurally controlled ones. I hate using that term because they're all structurally controlled. They all have some major structure which allowed the fluids to come up, and you typically some structure which has formed some sort of fold trap or a thrust trap above them to stop those fluids. The only difference really is the geometry. Are they horizontal or are they vertical? Okay, so then here's a look of Nevada, kind of zoomed in on the northern portion of Nevada. So this entire box is the Nevada Gold Mines box, where all the Newmont and Barrick properties are. And these are the major gold trends that exist. We have the Getchell Trend, the Battle Mountain Eureka Trend, the Carlin Trend, which was the first place Carlin-type mineralization was recognized, and the Independence Trend. Those of you going on the tour, you are going to be driving and camping down in here into Carlin, and then you'll come up here into Gold Quarry, and Kendall and the team will meet you and probably give you a presentation, and then you'll get to go all the way up into the North Carlin Trend. And so what we're going to focus on after I talk a little bit more about macro scale is that North Carlin Trend and the deformational sequence and structures that you'll be able to see. So if I take away those labels, all those black dots are areas of known gold and or copper mineralization in Nevada. This red line, this is the 706 line, so this is everything to the east of here is continental crust. Everything to the west of here is accreted rocks that took place post-Cordillera and erosion. This line right here is an approximate transition. It's called an isochron by Harry Cook. He's a sequence stratigrapher. Everything to the east of this line is platform carbonate. So your classic limestone that forms in warm, shallow marine environments, crystalline limestone. Everything to the west of here is transported slope carbonate. These are where the dirty carbonates are. Notice how these two features parallel each other. So when North America was rifted apart to begin with, and it became a passive margin, and the waters flooded in, then we started depositing limestone on top of our crystalline basement. And the spot where it transitions from that platform, the shallow water, into the slope, the deeper water, parallels this rift margin. The blue line is the eastern extent or limit of the Roberts Mountain thrust. That's where we thrust those silicious rocks up over the carbonates. So this is basically the easternmost extent of accreted terrains from Cordillera and tectonics. Notice how those things line up. And then finally, this V in here is where the northern Nevada rift took place at 10 to 14 million years old. And so hundreds of millions of years later, this pre-existing weak spot in the crust has decided to rift yet again, hundreds of millions after North America was rifted apart to begin with. So what does all this mean? Is there some sort of, why do we keep having major crustal scale features lined up in one spot in the crust? And why do we have hundreds of millions of ounces of gold and copper endowment along these spots in the crust? The truth is, we don't know. But we can arm wave, because basically all of the major gold camps or metal camps in the entire world pretty much are always on these massive crustal scale features. And these huge crustal scale features keep having repeated activities focused in these zones of the crust for hundreds of millions of years. So essentially what this is telling us is, for whatever reason, there's a weak spot in the crust, in the Earth here, and of the most important impact is that this spot in the crust is really connected to the mantle, because the mantle is the source for all of our metals. And so it's no accident that all of these gold deposits are lined up along this macro scale trend, and that we keep having macro scale geologic features, whether it be rifting, thrusting, sedimentation, they all keep lining up and being focused on these same areas of the crust. Okay, lithology and the resulting rheology. This is from Harry Cook's 2015 paper on the sequence stratigraphy of carbonate rocks across Nevada. And this is a diagram kind of showing what I've mentioned a few times. This is the reef setting where we're forming our in situ carbonate rocks, and this is our slope. And for hundreds of millions of years, we wind up depositing carbonate rocks like this. And during this time, sea level is going up, sea level is going down. And that's really important because it changes the nature of the redox state of the rocks that are being deposited, and it changes the nature of the slope rocks which are being transported. So when sea level is really high, then you're in a more reduced state of deposition. When you have wave energy, that wave energy is above this carbonate shelf, and it doesn't really impact the carbonate shelf at all. When sea level drops, now you're in a more reduced setting. And when these waves come in, they wind up interacting with this carbonate shelf, and they wind up sending tons of material downslope in the form of debris flows. So sea level's high, we have thin bedded muds of very fine grained material. Sea level is low, and we have coarse grained material with really thick bedded things. You can have debris flows that are 10 meters thick with boulders the size of this room in them. So what does that mean in terms of rheology? Basically, you wind up having two different types of rocks. So when you smash and deform these different rocks, different things are going to happen. So sea level high stand, low energy depositional setting, thin bedded rocks, fine grain. We squish those rocks, and they're just going to slip and slide. It's like you're on a conveyor belt. When you squish those things, they just want to whoosh. So these are the places where you typically wind up having thrust deformation take place. They slide along those thin bedded rocks, and then eventually they'll ramp up, and you'll end up duplicating your stratigraphy. Sea level low stand. Again, this is our high energy depositional setting. We get thick to massive bedded rocks, medium to coarse grain to macro grain. And when you squish these ones, they don't like to slip and slide that much. They like to buckle, and they like to fold. So now what you're doing is you're basically the amount of material in this, it's about 50-50 from the fine grain stuff to the coarse grain stuff. And some of it is just flowing like it's on a conveyor belt, and some of it is completely buckling. So the nature of what's happening to these rocks when they're being deformed is completely different. Finally, the platform boundary. This is the crystalline carbonate. This stuff is extremely massive. It doesn't have bedding, and it has interlocking crystals. It's really, really, really strong. So when we squish this stuff, it's basically like crashing into a brick wall, and nothing's going to happen. So all of these rocks that get squished and deformed when we're trying to thrust them, they come up to here, and they stop. And if we go back to this picture, this is the limiting exposure of that Roberts Mountain thrust. So when that thrusting event basically wound up interacting with that crystalline platform boundary, it couldn't thrust any further. And then finally, intrusive bodies. So we squish all this rock multiple times, we thrust it, we fold it, we fracture it, we repeat it, and we'll talk about each one of those events coming up here. And then the other thing that happens is we send hot intrusions up in. So remember in that schematic diagram, I talked about how all these major Carlin deposits, they always sit next to a Mesozoic intrusion. That Mesozoic intrusion is important for a couple of reasons. One, the type of intrusive rocks that these are, they're mantle derived. So they're coming up along these big crustal scale, massive structures that are connected to the mantle. Then that rock comes up and it winds up interacting with the carbonates. And it does a couple of things. One, it cooks the carbonate right around it. It sends off a bunch of hot metasomatic fluids around it that then metasomatize, which is a slightly different form of Hornfelsen. And that rock becomes harder when you do this. So that carbonate rock will fracture much easier once that rock is impacted by this metasomatism. Furthermore, if we squish that rock again, after that intrusive body has come in, that intrusive body, think of it as a big crystalline massive body. If you squish that, it's not going to want to do anything. It's strong, it's crystalline, and it's surrounded by rock that has tons of pre-existing weaknesses already. All the folding and fracturings that already took place, and all of the pre-existing bedding orientations. So now, when you squish that rock, all of that bedded rock, all the strain is going to focus around the sedimentary rock, and that intrusion is basically just going to sit there and be untouched. And the more you squish and deform a rock, the more you're able to crack it, especially if it's been metasomatized. The more you're able to crack it, the more permeable it is. The more permeable it is, the more fluid you can pass through it. The more fluid that passes through it, the more gold potentially can be in there, if the rock is the right chemistry, and if the fluid has gold in it. Okay, this is the Carlin Trend geology. So you guys who are going on the trip, you'll go right into here, the city of Carlin. It's right off the interstate. And the Carlin Trend runs from this area we call Rain, all the way down in the southeast, all the way up to northwest of Goldstrike. It's about 70 kilometers long, anywhere from 5 to 10 kilometers across. This spot in the crust has produced over 100 million ounces of gold. That means 100 million ounces actually poured and produced. When you process gold, your recovery on it is anywhere from 60 to 90%. So you can do some simple math on that and say if we produced 100 million ounces, that means that there's another 20-ish million ounces that are sitting in a tailings facility somewhere that we weren't actually able to process. So that's 120, 130 million ounces of gold. We have another 30 to 40 million ounces in the ground still. There's 160 million ounces of gold, probably, sitting in this spot here in the crust. And that's not even the most richly endowed spots in the world. There's a couple places in Quebec and in South Africa that are even more enriched than this. But it's probably number 3 in the world. So the simple map, all the greens are the siliciclastic thrusted rocks. They're the ones above the Roberts Mountain thrust. The blues are our carbonates, either slope carbonates, and then the purples over here, this is the overlap sequence. This is rocks, these are sedimentary rocks that were deposited on top of this as a result of eroding that Roberts Mountain thrust highland. And then in red is the outline of all the gold bodies. If we take a look over on this side, it just shows the major geologic structures in the zone. So this is zooming in from this black box in here. And you can kind of see how we have multiple different phases of folding. We have folds that are kind of north-south to northeast. We have macro scale folds that are northwest. And we have big crustal scale faults which trend parallel to the actual trend of mineralization. If anybody has any questions at any point, just make me shut up and ask a question. Very informal talk. You don't have to wait to the end. So if you want to hear more on anything or don't know what I'm talking about, feel free just to pipe up. All right. Now we'll take a look at this long deformational sequence that winds up controlling the distribution of ore in these carbonate rocks. So the first step is this Paleozoic deposition. So this is after North America has been rifted apart, and we're on a passive margin at this point. So this is a cartoon sketch. We have our platform, as I've talked about, and then as we grade out to the west, we have our slope rocks. Now, when we think about a passive margin, we always think it's about it not being tectonically active. It's a passive margin, there's no subduction, it's quiet. It's not really the case. Like most things in geology, in Geology 101, we tell you, hey, this is how it is. And then for the next 3 to 4 years, we go, actually, no, it's really like this. That's the story of geology. So these passive margins are actually extremely tectonically active. Because what did we just do to get this passive margin? We literally just rifted 2 continents apart. So as a result of that, we now have this massive rift and transform fault system that these carbonate rocks are being deposited on. Another thing, these rocks, which I think there's like 5 kilometers of carbonate rocks deposited in Nevada. Well, you know, even the Geology 101 students know that limestone only forms in warm, shallow marine environments, okay? So that means that you are going to deposit carbonate rocks in shallow water. Well, shallow, I don't have to be a mathematician to know that that's not very thick. Okay, so how do I stack up 5 kilometers of carbonate rock into shallow water? I'm just going to stack it up, stack it up, stack it up, and then I'm going to be above the water and I can't deposit any more rock. So what you have to think about is this rock, this crust, is extremely young. It just rifted apart. You have basalt rifts coming apart, and we're slowly pulling things apart. So this is very thin crust, it's very young crust, and it's very hot crust. So it's buoyant. It's thin and buoyant and young. And then as you slowly move further and further away from that rift boundary, it slowly starts to cool off. And then what do? You start depositing carbonate rock on it. You start loading the crust and loading the crust and loading the crust. And eventually it keeps pushing things down and pushing things down. It squishes and the crust keeps cooling and it keeps sinking and sinking and sinking. And so that's the process of how we wind up getting massive amounts of rock stacked up in what can only form in shallow water. Now, this rock, so not only do we have these pre-existing rift faults and transform faults, then the rock itself, as it's settling, it actually has to settle via tectonic process as well. So during this time, we actually have these big, massive normal faults, which form parallel to the rift margin and parallel to that platform margin. So from the very get-go of these rocks, we're actually putting a structural framework in them, where they're deposited on top of a rift, some sort of transformer rift structure, which is connected to the mantle. And then above that, we're putting these big, high-angle normal faults in them where the rock winds up settling and dropping down along normal faults. So from day one, we actually have a tectonic framework put in place in these non-tectonized slope and platform rocks. Okay, we get past the passive margin, the Cordillera orogeny starts to take place, and now we start squishing things. We're going to switch from a passive margin into an active margin. And this is where we're going to take those deep siliceous rocks that formed way, way out in the ocean, and we're going to thrust them on top of our carbonate rocks. And by doing that, we're going to form thrust faults, which wind up giving us yet another fluid pathway. And we're going to form ramp and thrust geometries, and we're going to form hanging wall anticlines and footwall synclines. So we've gone from having basically layer cake geology with high angle structures cutting through it, to now having thrusted and repeated layer cake geology with folds and faults. Phase 2, we have more thin skin deformation, and it's basically coaxial, which means it's squished in the same direction. And we wind up folding these things even more and thrusting these things even more. And we have spots exposed in the Carlin Trend where you can actually see that initial Roberts Mountain thrust, which came up and thrusted, has then been completely folded over and overturned. So whether this is a progression of the initial orogenic event, or we had a pause and then a second orogenic event is up for debate, doesn't really matter. What matters is that we keep squishing and we keep deforming these rocks. And the more folds we put into them, the more structural traps we're potentially putting into our favorable carbonate hosts. And the more thrust faults we put in, the more fluid pathways we have that can move up these gold-bearing fluids have them interact with our favorable hosts and favorable traps. Now we move into the Jurassic, and this is where we get the Mesozoic intrusions. So these intrusions on the Carlin Trend, most of them are Jurassic. There's one Cretaceous one. There's also Cretaceous ones that take place in some of the other Carlin type deposits as well. But basically just think of it, during the Mesozoic, we have back arc extension taking place, and these intrusive bodies are coming in. There's also huge dike swarms that are associated with these intrusive bodies that can be up to 30 to 40 kilometers along strike, and they'll follow this northwest orientation. So when you have dikes that you can trace for 30, 40 kilometers, and they're on a single orientation, what that's telling you is the crust is basically being pulled apart, ripped apart, perpendicular to that diking direction. And so this is where we're going to have our changes in rheology, where we're going to be able to cook these rocks around here, and these dikes are going to give us massive amounts of strike length, and that orientation just happens to be favorably oriented parallel to that slope platform margin as well. So now we have mantle connected dikes coming up next to our most favorable rocks and intersecting these different folds and thrusts. Finally, we wind up squishing these rocks one more time, and this is a post-Jurassic event, most likely laramide aged. This is a more thick-skin deformation, and by thick skin, we're saying that our reverse motion is focused along high-angle faults. So it's reactivating the normal faults that were open during the Jurassic and reactivating them as reverse faults, and forms really big, broad, upright folds basically across most of the Carlin Trend. So now we have these kind of smaller scale, more micro deposit scale thrust hanging wall traps, and then big, broad, open traps as well. So at this point, we've kind of given ourselves the perfect situation to be able to cap fluids if they're entered into the equation. Also during this time, this is the kind of the last phase of squishing and breaking and fracturing. And so all of that deformation that gets focused around those intrusive bodies, this is the time where those rocks just become extremely brecciated and permeable. And some of our deposits up in the northern portion of the Carlin Trend are so completely fractured and hammered where high angle faults run along the margins of these intrusive bodies. We actually have like a couple spots where we have 2 million ounces in about a 200 meter thick zone with a footprint that's only about 50 to 100 meters across, which is basically like finding a needle in a haystack. It's one of the highest grade deposits we have though. So basically where you have these spots where the rock is so fractured up, it becomes so brecciated, and you can put way, 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 way more gold into a rock. So this particular deposit winds up the average grade of it is like 35 to 40 grams per ton, whereas typically across most of the Carlin Trend, the average grade will probably be more like 1 to 10 grams per ton. Right? So it's anywhere from 3 to 30 times as endowed in gold because the rock is so brecciated, you can cram so much more gold into it. Finally, we move into the Eocene, and this is where Nevada starts to transition into an extensional environment, which it remains in to this day. And we basically start ripping apart all of the crust. So we have all of these pre-existing features. We have steep overturned limbs, pre-existing normal faults, pre-existing high-angle dikes. And now that structural framework is basically just going to start having massive amounts of normal fault offset superimposed on all of that pre-existing geometry. During this time, we have an extremely massive Eocene magmatism pulse, and this took place from Utah all the way across Nevada, and it sweeps all the way out into the ancestral cascades and even to the California border. These intrusive bodies are pretty deep. We've never actually seen them, the actual massive plutonic body itself. It only shows up in geophysics. So how do we really know it's there? One, there's a massive mag signature that's underneath all of these big Carlin deposits. We can see that it's about 10 to 15 kilometers at depth. Okay? We also have dikes, which come up and seem to kind of connect to this body that images along a geophysics signature. And we're able to date those dikes. And Mike Russell and Chris Henry have been working on them for the last 20 years. They date out at 36 to 40 MA. Okay? So how do we know that that intrusive body at depth is that age? So there's a guy named Ken Hickey who's spent about 10 years working on apatite fission tract dating around all of these major Carlin deposits. And all of the apatite fission tract ages around these deposits have all been reset to the same age as those dikes. So that's the indirect evidence we have of these massive intrusive bodies existing at depth. And it's that massive intrusive body that we're talking, the first thing I said, you need to have a system, you need to have a structure, you need to have a host. The system is inferred to be that massive intrusive body at depth. And whether the gold was in the crust already or the gold came up with that intrusive body, that the heat from that intrusive body pushed enough fluids up off of it, up into our rocks, and allowed the gold to be deposited. Okay, this is an animation, basically describing all of these events. So I'll go back. This is this spot, this entire zone from here up to the north end of the map. So the gold shows basically the outlines of the deposits. And this is the orientation of our platform margin and those growth faults, which were forming parallel to the rift at the time of deposition. And this is where all the gold is located. Then we have our Roberts Mountain thrust event. So we take this big thrust, we thrust it up against the platform boundary, and we wind up putting big folds in place. And this is where all the gold is. We then keep folding and keep thrusting it, and we wind up refolding these folds. We form more fold and thrust belts, which are slightly, just slightly more northeast than the north-south ones. And this is where all the gold is. We wind up having our Mesozoic intrusive bodies. So this shows the outline of where the actual stock is. And then in purple, the purple rectangles show schematically the distribution of the massive dike swarms which come along. Again, parallel to that platform boundary. And that's where all the gold is. Finally, we have this last laramide phase of deformation. We wind up putting big upright folds to the northwest of the stock, some other reverse faults scattered about, and there's a big reverse fault and fold located south of this schematic as well. Again, that's the relationship with gold. And then we move into the Eocene, and we're going to rip all of this stuff apart, basically along a northeast orientation. And that's the distribution of all the gold. So we need to have all of these events coalesce in the right spot in the crust, have them be structurally complicated enough, have them intersect carbonate rocks that have the right type of iron in them, then have a connection to the mantle and that deep intrusive source where that fluid can come up and interact with all these features. And this is just, I'll skip that one.
Can I ask you a question?
Yeah.
So you have two time periods where the engine's working, in the Jurassic and in the Eocene. Are those distinctive gold types?
So the Carlin system purists will tell you that all the gold came in the Eocene, despite the fact that there's evidence that there's Mesozoic gold out at Bald Mountain. We know for a fact our 4 Mile deposit in the Cortez district, which is our newest discovery from the last 6-7 years, we've actually shown that we have gold associated with bismuthinite that's associated with the Cretaceous intrusive stock there. Up at Gold Strike, those of us that have worked there have basically thought like, it can't be an accident that most of this gold sits right next to this. It can't just be from the ground. But the massive Eocene hydrothermal event is so overpowering that there's no like petrographic evidence. There's no SEM evidence from it because it all exists in those Arcinian events. So the massive bulk of it, from all the work that's been done, seems to be associated with Eocene, but the odds that there wasn't some bit of enrichment in the Mesozoic, I have a hard time believing that. And when you get in zones that didn't have nearly as strong of a Eocene overprint, there are zones, but it's typically more of an intrusion-related, kind of more skarn-related gold system, and it's not a true Carlin system, which happens, the fluids are more acidic, they're cooler, and they're a little shallower in the crust. But this one I will talk about because this is a little simpler one. So this is just an example of some of the work that we do as exploration geologists, where we've taken a bunch of structures. So this is a cross-section probably 2 kilometers away from a massive open pit, which also has an underground portal operation out of it. So there's an underground mine and an open pit mine, tons and tons of data. So as geologists, our job is to synthesize all of that data and figure out, well, if we projected along strike, what would the geology look like? So this is a cross-section we kind of put together, and then we put together, drilled these 3 really deep framework holes. They're probably about a kilometer deep, and we did downhole structural interpretation on them to try and figure out, okay, do the structures in the drill hole match and correspond with the structures that we see in the open pits? So we wind up synthesizing all that, putting it all together, and then trying to figure out, okay, where would be a good spot for us to target, right? So we like fold and thrusting stratigraphy. We like complex structural systems, big broad faults where there's big damage zones. We like places where we have our thicknesses of our units get thicker, because that potentially might mean that it's been duplicated via thrusting. We like to see, these are schematically showing what the bedding is doing in the hole. We know that from downhole structural and what the orientations of the dikes are. So we wind up piecing all that together and saying, all right, do I have the right structural story to put a gold deposit? In this particular interpretation, we had everything that we needed. What we didn't have is enough gold-bearing fluids. We had all the good rocks, all the good structures, all of the good dikes, but it just didn't see enough fluid. Because at some point, that fluid dissipates, and it's just not as strong. So it's our job as an exploration geologist to then say, okay, what direction do I have to go for the fluid's signature to get stronger? And in this case, it went to an area of ground that we don't control. And so we moved on to the next one. All right, any other questions? These are all just examples of deformed rocks on the Carlin Trend, like you guys are going to see this weekend. Yeah.
I have a few. So you guys work with gold and copper. Do you guys ever find other metals? And if so, what do you guys do with those?
If they're economically valuable enough and our processing plant has the ability to recover them, then we sell them. So one of our deposits, it's called Phoenix, it's outside of Battle Mountain, and it's very polymetallic, and so we're able to get copper out of that. And then we wind up having a sludge of a bunch of other random metals that some company in China buys for us. A couple of our deposits in the Carlin Trend are very silver rich, so it probably has a late kind of low sulfidation overprint on it. And in some cases, we're able to get that silver out. In some cases, the gold that we pour actually looks more silver than gold. So if we can pull it out easily, we can make money off of it. In some cases, we actually end up paying a penalty on it because the gold that we're selling to the place that buys our gold bullion, it's not as pure, and so they actually don't give us as much money for it. When we're actively exploring and we find, let's say we find something and it's got a bunch of gold in it, and then it's got a bunch of zinc and lead and tungsten in it, then the next thing we need to do is we need to take bigger samples of that, and we send it to our team of metallurgists, and we go, hey guys, what's up with all this other metal? Can we get it out? Is it going to impact our ability to get the gold or the copper out? You know, figure it out. And those guys are wicked smart. I don't know what they do, but they're full-on wizards. And so they do a bunch of crazy stuff in a lab, and they come back and go yay or nay.
So clearly incredibly complex geologic story.
Very.
2 questions. One, when was the first gold discovered there? And then secondly, how long did it take geologists to come up with that story? I mean, was it 100 years? Was it 10 years?
So the gold, the story in Nevada was silver first.
Yeah.
And then they started finding base metal things around these Mesozoic intrusions. There was
When?
Kind of like late 1800s.
Okay.
And then early 1900s, they were mining some of these things on the Carlin Trend where like there was a more, quartz vein associated gold, like that they could free mill and get out. It wasn't Carlin, above the Carlin system, and it was oxidized as well, so they could get it out. And then in 1960, they trenched across a series of dikes about 25 kilometers north of Carlin, and in one of those Jurassic dikes, they sent it for assay, and it came back ounce per ton. And they were like, what the hell? Because they couldn't, that was the invisible gold. They couldn't see anything in it. And so that was the very kind of first discovery, or not discovery, the recognition of this Carlin-type gold system. Thankfully, it was oxidized, so they were able to get the gold out. If the gold isn't oxidized, so and sorry for those of you who don't know, if it's oxidized, that basically means that the sulfides have been broken down. And so those Arsenian pyrite rims have been chemically broken down, and the gold ones have disassociated with the sulfide complex. If it's not oxidized, you have to send it to a big, crazy processing plant. Again, the metallurgists and their black magic, and then they figure out how to get that out of there. So 1960, that first Carlin mine came in, and then exploration was off to the races for about the next 25 years. So 1960 to the mid-80s is basically when all of the Carlin systems were discovered, and everything we've done since then has just been things that were much, much deeper. So they're either out in one of the basins of the Basin and Range, or they're underneath, like our most newest discovery, 4 Mile, is underneath a kilometer of upper plate rock. So we literally have drill rigs sitting at the top of a mountain at 8,000 feet, drilling 1.5 kilometer deep holes. And then what was the next question?
The question is, how long did it take geologists to come up with this story?
So this particular deformation sequence was done in 2015. A structural geologist named Dave Reese came, and this is before the companies were merged, and he was working with the Newmont geologists and started piecing together a lot of these geometries. And he spent about 2.5 years working with the Newmont geologists on it. And during that time, he came over to the Barrick properties. This is on the Carlin Trend, and that was while I was working there. And so I got to meet Dave. And he worked with myself and another Barrick geologist, and we were looking at all of the controls on the north part of the Carlin Trend that we control at Barrick. In the meantime, he was doing everything with Newmont, and he had CAs with both of us, so we couldn't talk about either one. And so this particular paper, he presented at GSN in 2015. He spent 2.5 years on it, and myself and other geologists contributed to it. And that was after 25 years of work. And he wound up having to get each company to run it through all the lawyers and say, yay, you can publish this, and then have to integrate the two, and then integrate all that stuff into a single paper. And yeah, he spent 2.5 or 3 years on that. And then we're still refining it to this day, right? The model works until it doesn't, and then we have to figure out, why doesn't it work here?
So, 2 questions. One, when I think of Carlin Trend production, I think of massive amounts of material that are needed. You can tell me how many tons are needed of rock in order to get an ounce of gold. That's also what makes it this parts per billion kind of.
Well, it's
not?
It's parts per million. So parts per million is the same as gram per ton, right?
Okay.
So and if it's oxidized, an economic Carlin deposit can be down to 0.5 gram, 1/4 gram if it's oxidized and sitting right at the surface. And because you can just send it to a heap leach, throw some cyanide on it, boom, gold, profit. If it's not oxidized, you need to be at about 3 to 4 grams per ton, because the cost of processing oxide ore is like $8 a ton ish, and the cost of processing refractory ore is $25, $30 a ton.
And then, but what's the most challenging environmental problems with that type of mining?
So anytime you're removing sulfide material, it's acid producing. And so all of our waste dumps have to be permitted. So anything that's going to contain acid producing waste has to be put onto some sort of a waste pile, which is lined. And so you can line that a few different ways. You can actually physically manufacture a barrier. Depending on how much sulfides is in the rock, you can actually just put it on a bed of inert limestone material, and that has enough buffering material to cancel out all the acid generating waste off of that. And then the other thing is that you can then backfill the actual pit where it came from. So because that pit will wind up becoming, once it's all shut down, it winds up getting capped off, and then once the dewatering is turned off, it winds up like being a lake. So we have environmental scientists and hydrologists basically monitoring all of these waste dumps. At the end of the year, any of us that run and maintain drill programs, we provide them all of our data so they know exactly what the inventory is of all the acid generating materials, all the metals that are in it. Same with all the rock that we pull out. So to be able to process this stuff, you have to wind up running for the metallurgists to do their black magic on it, they have to run a series of tests which say how much acid is in the rock, how much sulfur is in the rock, how much carbonate buffering capacity is in the rock, and so all that winds up going into a massive database, which is then stored, and we can say, okay, this rock is this acid generating or has this much buffering capacity, it has to go here versus there, and all of that dictates where that rock moves and gets put to. And it's all, like we have an entire compliance team that basically runs through all that each year, and then we report all that up to both federal and state regulatory agencies because our properties are on state land and or BLM land. And so we go through both regulatory agencies. And then we monitor all of our streams and all of our water wells. We maintain and drill water wells all around the property to see what is actually in those water bodies, basically 360 degrees around the deposit, 24/7.
So between like the mines and like your processing facilities, like how far away are they?
From here or from
Relative to each other? Like you have a mine here, like where's your processing?
Yeah, okay, so that was one of the big things with when we merged these two companies,
Yeah.
is in some cases we were driving rock a really long ways to a
Yeah.
processing facility when the other company had a processing facility literally right next door. So we were sometimes you have to drive things 20, 30 kilometers. Sorry, we're trained to think in metric, so so everything's in metric now, but it can be quite a ways. Ideally, you find a really, really big deposit, you put the processing facility right next door.
Okay.
But then you keep finding satellite deposits and they can be further away. For instance, the Cortez camp, there is no processing facility because most of Cortez is oxidized. So they just have a mill and a leach pad. But then when they get below the redox boundary, all of that ore has to get shipped to the Carlin Trend, and you're looking at 20, 40 kilometers in trucks. And so the grade has to be really, really high in those deposits to offset the cost of driving it that far. But we have we have three major processing facilities in Nevada, and basically any other company, if they were even to find a small Carlin deposit and it was refractory, they're never going to be able to afford to build one of those plants, and I don't think anybody will ever be able to permit one of those plants ever again. So essentially, any refractory Carlin type ore that gets discovered in Nevada, they would have to make a deal with us to process it at our facility.
How long does it take to process like a ton of material?
It's a good question. I used to know the answer. I think it's it's on hundreds of ton at a time, but a batch is probably in the neighborhood of like from mill to out the door, I think maybe like 24 to 36 hours in the roaster. And the roaster, think about a roaster as like an oven.
Yeah.
You basically cook it and you burn off all of the material. And then we also have a process called an autoclave, which is like a pressure cooker. And that one takes longer because it actually sits in a tank and it's pressure oxidized for like 3 days, I think. And so you basically do like 3 million years of oxidation that would occur in nature, and you do it in like 3 days. So that one takes longer. It's one of the reasons it's more expensive.
Yeah. Another question. So how long does it take from like going from, oh, we're gonna go like explore an area to, oh, we find something? Like how long is like the development?
Okay, so let's say, like I would say, you could spend anywhere from 1 to 4 years acquiring the property if you don't have it, sampling it, putting maps together, resampling, and then starting to put drill holes in. And that's probably about a 4-year process, and then either you're onto something or not.
Yeah.
So you could get, if your initial samples suck, you're just done and walk away. But if it keeps looking good, you're probably up into about 4 years of doing all that, and then you're drilling it and you're going, okay, we got something. Then you'll probably spend another 2 to 3 years drilling and drilling and drilling and deciding how big it is and how it could be mined. And during that time in the background, all of the lawyers and environmental permitting people would be going, okay, if we want to do this, like we got to do this and this and this, and there's tons and tons of regulation on that.
Yeah.
And so the regulatory aspect would probably take anywhere from 6 to 12 years. So that's probably going to start at that 4-year window. So from 0 to in production, I think your best case scenario in today's permitting environment would be like 12 to 16 years. And a lot of that is like just the actual, like you have to drill it and know it's there.
Yeah.
And then it kind of it transitions away from the discovery and refinement and into the bureaucracy and logistics.
So do you only do the do you only do the exploration and sampling, or do you also help with processing as well?
So it depends on what your job role is. So I've worked everywhere from a production geologist that was pit mapping to ore control to geologic modeling to drilling out the deposit proximal to doing exploration where I'm often like random places all over North America. And so you wind up, depending on what job role you're in, once the exploration team has kind of gotten it to that 4-year stage where it's like we know it's there, we've drilled it out, we know there's continuity, at that point it typically winds up being handed over to the mine group, which then does the rest of the drilling and actually brings it into production to where you can actually pull the grade out. There's a little bit of overlap of like a year or two because you kind of have to pass that knowledge on. The people that were working on it really understand it, and the people that are coming in, they just got there.
So you said like companies merge together. How did that like affect like the overall like process of things getting done? And how did that affect you as a geologist, like as a scientist? This whole business thing.
I'm not gonna lie, it was chaos. So different people handled it different ways. I was like, oh, whatever. I'm a geologist. I look at rocks. It's like whatever. I kept getting paid. Other people, definitely had a harder time dealing with it. It was really complex. There's a million moving parts. Some of it was seamless, and some of it took a year or two to figure out. Like especially these different processing plants. They were built for specific rock types with specific chemistry. And so in some cases we were like, oh, we started bringing rocks from over there, and we were like, oh, wait, that chemistry is pretty different. So we had to kind of modify the plants and really figure out. Now we have way more equipment, so we had to figure out, where's the best place to utilize the equipment. Even just figuring out which company's policies you kept, like they had different benefits, different vacation, different so there was a million things to figure out. And I think we're 4 years into it now, and everything's kind of worked out. But it was complex. I think the most difficult part that we still have a few hiccups on was the database. And we have hundreds of thousands of drill holes, and it's all stored in a database. We have these database teams, and you have to be able to figure out like where all that data lives and how to extract it and make sure that it's all in the same coordinate system. Unfortunately, most mines they use local projection systems. I don't know if any of you guys know about GIS, but there's UTMs and lats and longs. Well, mines just basically go, oh, here's my mine grid. I'm starting at an origin of 0, 0. And it has its own local projection, and they're all different. So we had to figure out how to get them all like into the same projection system. So when you extracted all of the data, it plotted up in the right spot. So I think that was probably one of the more challenging pieces of thankfully we have a lot of really smart people that are able to figure out the problems.
So you mentioned like this particular like job type kind of takes in like all the different aspects of geology, from like structural, everything. Do you think that like makes it more of a like challenging thing to do, or does it kind of just, is it like even better to be able to put everything together to do like your job?
For me, it makes it more fun.
Mm-hmm.
Like, I love my job. Like, I literally am excited to do every bit of my job, and that's the one thing I can, if I'll pass any advice on to anyone, no matter where, no matter what you major in, what your exact degree winds up and where you wind up working, find something that you enjoy. Because once you're my age, I'm 45, I got 2 kids, all my friends I made in college are scattered all over the whole country. If I'm lucky, I see them once a year. My best friends are the people I work with and my kids now. So the fact that I love my job and I have all of these fun little puzzles to figure out, I have to figure out the stratigraphy, I have to figure out the structure, I have to figure out the igneous story, the alteration story, and then figure out if the chemistry works. Like, to me, it just makes it extremely fun and rewarding, and it's never monotonous. You never wind up just doing the same thing over and over. So that's what I love about it, and it makes it so I'm stoked to go to work every day.
That's a great way to close it out. I love the message.